But she's from Torino, so please, the floor is yours.
Thank you. Thank you, Jan, and hi everybody, and thank you for the organizer of the event for this nice opportunity of giving this talk. Today I will talk about the geometric approach to supergravity in superspace, and especially about some of its application and some work that I'm now working on with the supergravity research group at Politecnico di Torino. Niemann and Regge developed in 1978 a new approach to supergravity, which was based on Cartan approach to gravity. It was an extension of Cartan approach to gravitational theories in the case of supergravity. And in this approach, the theory is constructed on a whole supergroup manifold, which defines the Lie algebra value gauge field in the coadjoint representation of the supergroup. And this was further elaborated then by different research groups, in particular by the supergravity research group in Turin. And it is now known as the geometric approach to supergravity in superspace, or the aeronomic approach. So today I will just give you some key aspects of the geometric approach in superspace, and as references you can take this Castellani Lavera book or a review by Riccardo Dauria. And then I will discuss some application in the context of higher dimensional supergravity in the geometric approach, in which case we have the emergence of what is known as free differential algebra structures, supersymmetric free differential algebras, that are known in the mathematical literature also as Cartan integrable systems. They were developed in parallel with the let's say supergravity school. We have the free differential algebra. In parallel we had Cartan integrable systems developed by Sullivan, and nowadays they are included in the theoretical mathematical framework of strong homotopy algebras and then infinity algebras. And in particular, they appear when we are dealing with higher dimensional supergravity theories, since we have to deal with higher degree differential forms. And I will explain how in the geometric framework it was unveiled and studied the hidden gauge structure underlying the free differential algebra described in the vacuum structure of supergravity theories. In particular, in this context, we have that the extra one-four fields appear. They are dual to, they are bosonic and spinorial one-four fields, dual in the Murray-Cartan description to algebraic to generators of the superalgebras. And in particular, I will give you the example, the explicit construction, the algebraic construction, in the case of 11-dimensional supergravity, which was the framework, the theory in which this was studied for the first time. But this, the hidden description of free differential algebras can be is fully general, can be extended to any supergravity theory in any dimensions. And this will be based on a work by Lucrezia Ravera of 1982, and by a recent results in which we have clarified the group theoretical role of the extra one-four fields appearing in the theory with Laura Andreanopoli and Riccardo Dauria. And finally, I will discuss how these hidden forms appear also in other contexts to solve problems that are apparently completely separate from the disclosure of the hidden structure of free differential algebras, in particular in the context of the boundary problem in supergravity, and in particular in the vanishing cosmological constant limit. And how this construction results to be somehow related to, it appears to be related to the off-shell construction of supersymmetric theories, in particular in this context of supergravity. And this will be is still a work in progress, and I will then give you some upper directions. In this second part of the talk, I will focus on the case, in the simplest case of n equal 1, d equal 4 pure supergravity, that is where we have more hints, more insights regarding this construction. So first of all, we work with differential forms and with dual Lie superalgebras, and therefore Murray-Cartan equations. we have a Lie superalgebra, okay, which can be written in this way, where Ta are the generators in the adjoint representation of the group. It can be dualized in this way by including differential one-form fields, and therefore we have that the Murray-Cartan equations emerge, where the D2 closure of the Murray-Cartan equation correspond to the Jacobi identities of the algebraic framework. Then we can switch on, and this is what is called, it's commonly referred when we deal with the whole algebraic structure underlying supergravity theory. We would say that in this framework we are attached, let's say, to the group manifold, while we can then move to the supergroup manifold, switch on curvatures, and therefore, in this case, in the case of supergravity theories, this will be supercurvatures or superfield strengths, and they are the building blocks of supergravity in the geometric framework. While for the Murray-Cartan equation, that is when we have that the supercurvature R0, we are dealing with the vacuum structure of the theory. In the geometric formulation in superspace, we are dealing with superspace, and so the theory is not formulated on ordinary spacetime, but we also have fermionic directions, and then one can, of course, restrict to spacetime. And superspace is spanned in this formalism by the superfieldben, which are composed by the fieldben and the gravitino, and they are respectively dual to spacetime translation and to Q, that is the supersymmetry generator. Here I will be, I'm omitting R symmetry indices for simplicity, so we will focus on the n=1 case safe in this talk. So these are some key aspects of the geometric approach to supergravity in superspace, and then once I will introduce the boundary problem. So now we will first focus on the free differential algebra, that is on the vacuum structure. In this first part, I will just focus on the free differential algebra description of the theory, that is on the vacuum structure. But then I will discuss the Lagrangian and the action. So I will explain and introduce the features of the geometric approach. Yes?
So this psi is a spinor for you, right?
Yes, precisely. It's the gravitino in supergravity. Yes, it's a spinor.
So you are interested at the same time in the sense you are interested for fermionic supergravity?
Yes, we have, yes.
Okay.
We have the superfieldben, which is, yes, we are working in superspace. We have Grassmannian variables. So, and indeed, we have superfields, which depends both on x and theta, where theta are spinor anti-commuting coordinates. And we are introducing a base space, the base space of superspace, which is spanned both by the bosonic fieldben and the fermionic one, that is by gravitino. So, okay, in the superspace we have superfields, the supercurvatures, and then we can restrict to spacetime, give the ordinary description on spacetime by restricting to theta d theta equals 0. In principle, one has extra dynamical degrees of freedom in superspace, and so we have to introduce some constraints to have the same dynamical information in superspace that we have for the theory once it is developed in spacetime. In the geometric approach, these are called the rheonomic constraints, and they are implemented on the parameterization of the supercurvatures. What happens in this approach is that the Bianchi identities now become some relations among the superfields and their curvatures that are satisfied on shell. And this is realized by requiring that once we have defined the supercurvatures that are defined of shell, they have to be identified on shell. So once we consider the equation of motion, we implement the equation of motion, the supercurvatures that have to be identified with two forms in superspace. So they acquire, we say, a parameterization on a basis of two forms in superspace. And the full parameterization is determined by requiring that the Bianchi identities that now are relations have to be satisfied. This is the expansion of the curvature that we give on the basis of superspace, so given by the Philben and the Gravitino one forms. We call those components along two bosonic Philben the inner components, and those along at least one fermionic one form field the outer components. So by requiring the curvature to fulfill the Bianchi relation on superspace, now we get that the outer components are given as in terms of linear tensor combination of the inner components. And these are some constraints that are physically, one can prove that these are completely equivalent, physically equivalent to the on-shell constraint that is to the field equation of the theory. So we don't have any extra degrees of freedom in superspace with respect to those that we have on space-time. And in the geometric approach to supergravity, to supersymmetric theory in superspace, in particular, we have a geometric understanding of supersymmetry, in the sense that supersymmetry transformation of the fields on space-time correspond to diffeomorphisms, but in the fermionic direction of superspace, and so they can be written as Lie derivative in those directions. And this is a powerful aspect of this formulation, as we can have in superspace, in general, in superspace formalism, and in particular in this context, in the geometric approach, we can have an understanding of supergravity in superspace that is analogous to the geometric understanding that we have for gravitational theories on space-time. This is an example, just to show, which is then the explicit formulation in the n equal 1, d equal 4 pure supergravity case, in which we have a set of one-form fields that are the Philben, the Gravitino, and the spin connection. We have the associated supercurvatures, that is the Lorentz curvature, the torsion, and the Gravitino superfield strength. And then they will appear in the Einstein-Hilbert plus Rorita-Schwinger-Lagrangian in this way. And the Lagrangian is a four-form in superspace. And then one can restrict the theory to space-time and write and see that we have precisely this correspondence between the theory in superspace and the theory in space-time. And the Maurer-Cartan equations of the theory then define the vacuum of the supergravity theory, and so when all supercurvatures are set to 0. So now I will move to higher dimensional supergravity in the geometric approach in superspace and discuss free differential algebras and their trivialization in terms of one-form fields. I will be a bit sloppy in naming one-form fields and generators, in the sense that we know that they are related by a dual description, so one-form fields and generators, but just to give you the whole construction. So in the context of free differential algebras, they were introduced, as I told you, in the context of higher dimensional supergravity theories. And why we have those structures underlying supergravity theories in higher dimension? Because in those theories we have P in the antisymmetric tensor, which naturally appear in higher dimensional supergravity theory. They are described at the level in the language of differential forms in terms of higher degree differential forms. And therefore we need some framework to generalize the Maurer-Cartan equation to the presence of higher forms. And these are called Cartan integrable system of free differential algebras. And this is done by incorporating p-form gauge potential. So the step for constructing a free differential algebra, which describes therefore the vacuum theory of higher dimensional supergravity theories, is that we start, given a set of Maurer-Cartan forms, then we can build n-form cochains in this way. And then if there exists some p such that we can write a cocycle based on p plus 1 form, then we can introduce a p-form gauge potential and write this relation. This is the vacuum structure, and this is the higher form field strength associated then with the p-form gauge potential. And so once we have built this structure, we can consider as a new basis of, let's say, generalized Maurer-Cartan forms, that is involving both the Maurer-Cartan one forms and this deformed gauge potential that we have introduced, and look for new cocycles in an iterative way by building the whole free differential algebra. The cohomology structure, the cocycles in superspace can be particularly involved, and under the mathematical perspective, the construction is still in process, and one can go very high with forms, but with form degree. But under the physical perspective, there are constraints given by the dimensions of the theory that one is considering. So there are constraints on the physical meaning of p-form gauge potential related to supergravity and supersymmetry theories in general. For the case of that we are going to analyze, so the case of the free differential algebra underlying 11-dimensional supergravity, I will show you what was the Ravera program for trivializing the free differential algebra associated with 11-dimensional supergravity in terms of a hidden Lie superalgebra. So the field content of the theory in 11-dimensional supergravity is given by the metric, a free-index antisymmetric tensor, and the gravitino. The space-time action was built by Kramer, Julia, Scherk, and then the theory was reformulated in the geometric approach by Daure and Frey by considering the presence of a three-form gauge potential associated with the three-index antisymmetric tensor. And so the free differential algebra underlying the theory was introduced and investigated in details, and they also built the Lagrangian Lie action within the geometric approach, switching on the curvatures, the supercurvatures associated with this free differential algebra. We have the Lorentz curvature, the torsion, the gravitino field strengths, and this three-form gauge potential whose field strength is a four-form. The D2 closure of this structure relies on three spinors fierce identities, in particular in this one, which are crucial objects in the construction of the vacuum structure of supergravity theories. And beside, one can also introduce, and this is always related to the presence of some fierce identities, can introduce a six-form gauge potential whose field strength is a seven-form. And this seven form is Hodge dual to the field strength of the three-form gauge potential on space-time. Commonly, the dynamical theory is built by using the three-form gauge potential, and it is I've never seen it explicitly in the literature, but what is expected is to have a dual description, say like electric and magnetic description of the same theory, but in terms of the six-form gauge potential. And so we can say that the whole free differential algebra underlying the vacuum structure of the theory is given in terms of these fields, and it is invariant under p-form gauge transformation and those are the gauge transformation for the three-form and the six-form, and these are the p-form gauge parameters, the two forms and five forms. Then the Daure-Frey investigation was, can this free differential algebra be treated for an ordinary Lie superalgebra in such a way to describe it in terms of objects that we know how to deal with when we are dealing with superspace and with Maurer-Cartan forms, with one-form fields. And so they associate, the answer is yes, they associate with the three-form and the five and the six-form two one-forms that are antisymmetric in the Lorentz indices. And they took as basis of Maurer-Cartan forms the whole set of fields, now including these extra one-form fields with extra Maurer-Cartan equations. And then they assumed to have the three-form written in terms of an ansatz, let's say, in terms of these one-form fields with all possible combinations, and then to these ansatz to fulfill the vacuum free differential algebra on ordinary superspace. It turns out that this is not enough. One also have to introduce, for a enough, one also have to introduce, for a supersymmetry, some auxiliary spinor one-form field, obeying whose covariant derivative is defined in this way, obeying this constraint for the D2 closure in vacuum. And then the parameterization of the three form, fulfilling the three differential algebra structure, results to be given in terms of, in this way, and we have one free parameter. So once we have this construction, we can describe, we have these one-form fields, so we know that we have those extra bosonic one-form fields and one spinor extra one-form field, and to describe the three form appearing in the theory. So we know that we can move to the dualize the description in terms of generators, and in particular Q prime, that is the generator dual to eta, is nilpotent, in the sense that Q prime with Q prime anticommutes in this way. And then we can write the hidden superalgebra underlying the theory. ZAB and ZA1A5 were understood as M-brane charges, sources of A3 and B6 respectively. The role of this extra fermionic generator Q prime introduced in the theory was understood later. I did this works in collaboration with Laura Andrea-Napoli and Riccardo Daura. And in particular, we proved that its presence is crucial not only to reproduce the supersymmetric free differential algebra in ordinary superspace, but it behaves as a homological, let's say, ghost for the p-form gauge invariance, in the sense that it projects out of the physical spectrum of the theory the non-physical degrees of freedom, and it allows a fiber bundle structure in intertwining between basis and fiber. And with this construction, we have the p-form gauge transformations are realized as diffeomorphism in the fiber direction of the group manifold. So this is the way with respect, there is another algebra which is well known in the context, again with 32 supercharges, and well known in the context of supergravity and superstring, that is the M algebra. For that algebra, we have some extra bosonic generators, that are ZAB and ZA1A5. And what happens is that if we consider, we can see that the presence of the extra fermionic generators appearing in the 11-dimensional supergravity theory allows to build, to project out of the base space those extra bosonic one-form field and project them in the fiber in such a way to get rid of those non-physical degrees of freedom in the context of 11-dimensional supergravity. So it is a kind of intertwining generator between basis and fiber. So this is the construction essentially at the level of the Lie superalgebra. We have a principal fiber bundle structure in which we have that the base space is just given by the superfield band, so ordinary superspace, and therefore the free form written in terms of one forms fulfill the free differential algebra on ordinary superspace, just spanned by the superfield band, while the fiber is generated by HH0, that is Lorentz, plus those two extra one-form fields. And so this is in this sense that we meant a kind of homological ghost field projecting out of the physical superspace, out of the basis, those non-physical degrees of freedom. We also have a singular limit in which the free differential algebra lives in an enlarged superspace, and this the one for this spinor is set to 0, but is a singular limit that we didn't analyze yet in detail. This is the study of the gauge invariance of the free differential algebra, so the structure that we have introduced to trivialize the free differential algebra in terms of one forms. We have that the gauge invariance of the free differential algebra require this gauge transformation for eta. And then what it turns out that once that we have written the whole free differential algebra in terms of one form field, including the extra spinor, we have that in the presence, in particular of these extra spinor, the gauge transformation of the free form written in terms of one forms is realized as a diffeomorphism in the fiber direction of the group manifold. The same is expected to hold for the sixth form. We don't have a complete algebraic trivialization of the sixth form yet, since calculation at the algebraic level are rather involved. So this tool was to study supergravity, was a tool to study the free differential algebra underlying supergravity theories in vacuum, and to trivialize this structure. We have seen that the same hidden forms also appear in another context, that is the boundary problem in the case of flat supergravity. The boundary problem is I don't know how many minutes.
About 1 minute.
Okay, so let me just, okay, we can define the action and the Lagrangian in the geometric approach in terms of forms, one forms in particular on superspace. And what we have is that once we consider the supersymmetry transformation of the theory, we have to have supersymmetry invariance, and when we are, this is the necessary condition for a supersymmetric invariant Lagrangian in superspace, where epsilon is the supersymmetry parameter, and this condition emerge due to the fact that we have that in the geometric approach to supergravity in superspace, the supersymmetry transformation can be seen as Lie derivative along the fermionic direction of superspace. When we are in the presence of a non-trivial boundary, on a manifold with boundary, commonly what happens is that supersymmetry is broken. And so we have to restore it, and the procedure, the standard procedure which was introduced in the literature, is to introduce some boundary term, consider the full Lagrangian, and have this particular constraint emerging at the boundary for the full Lagrangian. The particular case of vanishing, and this is something that works perfectly well in the case of non-vanishing cosmological constant. The limit in which the cosmological constant is set to 0 was not well defined. We studied it, and we have seen that it is possible to restore the invariances of the theory in the flat case, let's say in the absence of an internal scale in the Lagrangian, so in the vanishing cosmological constant limit, by introducing some extra fields, again, a one-form field and a spinor one-form field. And we have just shown that within this geometric framework, it is possible to restore the supersymmetry invariance of the Lagrangian by including those fields in the boundary. It turns out that the same fields are those that trivialize the free differential algebra of four-dimensional supergravity in the presence of a three-form gauge potential. And if we count their degrees of freedom, we also see that they allow for the off-shell matching of bosonic and fermionic degrees of freedom. And so we can say that we have obtained some topological, in the sense that they allow for supersymmetry invariance in the presence of a non-trivial boundary, auxiliary, in the sense that they allow for the off-shell matching of degrees of freedom, hidden, because they are the hidden fields, the hidden one-forms underlying the vacuum structure of the theory, one-form fields. And so the open direction now are extend this construction to more involved supersymmetric model and extend the study to the whole free differential algebra underlying supergravity and supersymmetric theories. Study the out-of-vacuum theory, possible connection with superspace formulation of shell supersymmetry theories, and to possibly describe this algebraic construction in which computations can be also particularly heavy in a mathematical geometric framework associated with Cartan geometry and supergeometry involving higher structures. So, okay. Thank you.
Thank you very much. For a quick question, if there are some. Please.
At one point, infinity algebras were mentioned. I don't know, maybe maybe I missed a problem. Did I visualize something? But where and how do they come into play here?
Sorry, I didn't get which
Where
structure.
and how do L-infinity algebras come into play?
In the free differential algebra constructor, because free differential algebra is was a way to name Cartan integrable systems, and nowadays the whole construction involving higher forms can be embedded within the framework of strong homotopy algebras. So this is just the mathematical, the algebraic way of dealing with those structures at the supergravity level. But and we are now trying to reformulate in a more abstract, generalized mathematical way these constructions, and so yeah, in the context of yes, and infinity algebras and higher structures.
Thanks. One more? Or two more then?
No, if you had to choose one, what is the main advantage of using free differential algebras instead of using the usual super Lie algebra approach?
In one sense, okay, for free differential algebras, they naturally emerge in a sense that you are driven by, because you have the presence of higher degree of tensors with p-index antisymmetric tensor. They are associated with p-form gauge potential, so you have to introduce them in a sense. And then you can deal with them geometrically, build the Lagrangian and study it. But at the geometric level, the geometric understanding that we can have of the theory, it is better, in a sense, to deal with one-form fields, with Lie superalgebras rather than and they also allow the hidden structure underlying the theory seem to allow, at the physical level at least, a reshuffling of the bosonic and fermionic degrees of freedom in such a way it's not unique, the trivialization, and there can be this again at the algebra level combination. A possible combination allowing for the off-shell matching of degrees of freedom involving, and also they are not, and also due to the presence in particular of fermionic, of spin or one-fold fields that don't have spin 1/2 but spin 3/2, so can circumvent noble theorems in the context of the off-shell formulation of the supergravity theories.
So, thank you. There was last.
Can you briefly tell what do you mean by Cartan integrable systems?
Yes, essentially I mean I used to call them free differential algebra, that is to say extensions. I know that they were introduced by Sullivan in parallel, and in parallel by the free differential. They were called free differential algebra by Riccardo Dauri and Pietro Frey when they were studying these structures. They just didn't know of Cartan integrable system. They are the same structure in the sense that they are a generalization of the Maurer-Cartan equations to include higher degree differential forms. At least this was the way in which they were. It might be that at the mathematical level, it might be that I'm missing something. But what happened, it was that once these free differential algebras were introduced, it was noticed that okay, something on the same footing already existed at the mathematical level, and were Cartan integrable systems.
Thanks. So, well, no. We postpone all the other questions to the coffee break, and let's enjoy coffee break for 15 minutes now.